Hello everyone and welcome back to this NPTEL course on aquatic geochemistry. We had been discussing strontium isotope system in our previous lecture, and in this particular lecture we are going to continue discussing another radioactive isotopes, that is the samarium neodymium isotopes. Now, samarium 147 has only 15% abundance and is having another 4 other isotopes. Samarium decays to 143 neodymium after a alpha decay, okay, with a half life of 106 billion years. So, an extremely long half life, right. And samarium neodymium is the compatible, incompatible. In those terms, it is just the opposite of rubidium strontium system. Okay. So, in the rubidium strontium system, my rubidium was an incompatible element. That means, it was getting out of the earth, inside the earth from the mantle, as when the melt was happening, whenever there is creation of magma, my rubidium from the mantle will go to the magma and therefore get enriched in the earth's crust. Samarium on the other hand is a very compatible element. Okay. What do you mean by it is a very compatible element? That means now this particular element prefers to stay in the mantle, it does not like the melt phase. Okay. So, it will preferably stay in the mantle as compared to the melt. So, the melt is more samarium depleted. Therefore, in the earth's crust, samarium's concentration is very low. Therefore, the concentration of radiogenic neodymium is also very low. Okay, just the opposite of rubidium strontium. So, here samarium is a more compatible element. Therefore, wherever the compatible parent is more available, the radiogenic daughter will also be more. So, if we see the terrestrial materials, you will see garnet which hosts a lot of samarium. Okay. The samarium neodymium ratio is very high. Okay. Morb, that is the basalt found in mid-oceanic ridges. So, mid-oceanic ridge basalt, that will also have higher samarium by neodymium ratio. Okay. Sea water ratio is this. In shale, which is it is a kind of sedimentary rock, okay, that sedimentary rock has a value of 0.209, and in solar system the value is this. Okay. So, this is more related to how the primordial samarium neodymium could have been. Okay. So, interestingly, as you can see is that mantle related mantle related rocks have more samarium by neodymium ratio. Okay. So, therefore, these particular rock types and minerals, they will have more radiogenic 143 neodymium. Okay. So, when we are writing the decay term, this is the equation that we write. So, 143 neodymium, the stable isotope is this one, that is 144 neodymium, and we have the initial 143 by 144 neodymium plus the decay term, that is 147 samarium divided by 144 neodymium into e to the power lambda t minus 1. Okay. So, this is our decay equation for dating. Okay. So, morb, which is our more mantle derived materials are getting accreted here. It is coming out from all these mid oceanic ridges. They are going to have very higher 143 neodymium concentrations or radiogenic signatures. So, if we are seeing a similar plot as we have seen for strontium isotopes also, we are going to plot 143 neodymium by 144 neodymium on the y axis, and on the x axis we are going to plot the time. Okay, we are going to plot time, and this is over billions of years of scale. So, throughout Earth's history, how neodymium isotopes have changed. So, as we always begin, so we begin with the bulk earth value, which is the average earth value. So, this is the bulk earth value, okay, undifferentiated average value of the earth, and how it has evolved, okay, how it has evolved. So, this is the bulk earth value and how it should have been after, this is how it should have evolved if earth would not have differentiated at all. Okay. But earth got differentiated, and earth now has different crust and mantle signatures. So, when crust got formed, it started having lower samarium. Okay. It did not have much samarium because samarium is a compatible element. So, it did not have much samarium. So, therefore, during the differentiation, our crust has started with a very low samarium concentration, and therefore, the samarium, the neodymium isotope ratio of the earth's crust is also low. On the other hand, the mantle has higher samarium by neodymium ratio. Mantle has a higher samarium neodymium ratio, and as it is getting continuously depleted, the mantle is slowly getting depleted. Depleted means it is melting, some of the melt is reaching the crust. Okay. So, this is called the gradual depletion of the mantle. As the mantle is getting depleted, more and more samarium prefers to stay in the mantle, right. So, the more depleted mantle is having now more and more of samarium. If more samarium is there, chances are the decay product will also be higher there. So, 143 neodymium is also highest in the more depleted mantle. So, now the more depleted mantle has a signature of 0.514. Okay. So, this is how the mantle and the crust differs in terms of neodymium isotopes. Okay. So, it is just the opposite of rubidium strontium system. So, here if you see that the crust has a lower radiogenic value, that is more unradiogenic, and the mantle is more radiogenic. Now, since in terms of values, we see that the differentiation is happening, the differences are in the third decimal place, fourth decimal place. There is another particular notation in which we write neodymium isotopes. So, we write in this epsilon notation. Okay, what is epsilon notation? Here we are standardizing it with a particular standard which is called CHUR, CHUR, which stands for chondritic uniform reservoir. Okay. So, this is from a particular chondrite value that we take as a reference point. Using that as a reference point, we are going to calculate all other rock types on the earth. Okay. So, we are having the 143 neodymium by 144 neodymium of the sample divided by 143 by 144 neodymium of that particular reference point, that is CHUR, minus 1 into 10 to the power 4. So, this helps us get rid of all the large decimal places. Okay. It also gives us a reference point, and it also helps us get rid of all the decimal places, and now we can only talk about in some positive integer values like +4, +8 to varying up to +12. And if you are having a crustal value, that will be more of the negative, because now this CHUR is our 0. So, anything which is less than that value will have a negative signature. Okay. Now, how do we use neodymium isotopes? Okay. Now, neodymium isotope, the residence time of neodymium in the ocean is around 400 to 900 years. What does it mean? Residence time of neodymium in the ocean is 400 to 900 years. That means it is less than the residence time of water in the ocean with an average of 1500 years. So, that means if there is a particular event happening here near the Australian coast, then that will not get mixed immediately, that is within the residence time of neodymium, okay, as the water gets mixed. So, as the entire water gets mixed over in the ocean and all, that it will that has a higher mixing time or residence time as compared to the neodymium isotopes. That means, with neodymium isotopes we are able to see a lot of differences in the different regions of the ocean. Okay. So, in this plot we are seeing some dots. Okay. These dots give us the epsilon neodymium value. So, as you can see, it can vary from 0.0 to minus 15. Okay. That means more and more crustal signature, this is more and more morph signature, and with that it has been plotted with the global ocean currents. Okay. It has been plotted with the global ocean currents, because that also determines how it is mixing. Okay, how the isotopes are mixing, and how different regions have a particular signature. Okay. So, for instance, if it is more red here, okay, it is going to be more red in this direction also, because yes, it is this kind of mixing is happening, and there is a lot of upwelling, downwelling. So, the red ones, okay, they are the hot currents, okay, warm currents as we call them, and they are the more shallow currents. While the blue currents, they are the more deeper currents, they are the cold currents. So, we have a vertical mixing and we have the spatial mixing. So, when we are using such isotope systems, what helps us understand? It helps us understand as a tracer of ocean currents, how it is mixing in the different ocean masses. It helps us identify separate ocean masses, okay, something that is not very well mixing. Okay. So, in the oceans, imagine how do we how do we differentiate between the ocean masses? There are different mixing places. Okay. Oceans come, they will meet, there will be hotter current, cooler currents. So, we need particular tracers for that, right, and very often the mixing happens such that they are having overlapping ranges and all that. Okay. If you are looking for concentrations in your sodium, magnesium, calcium and all these values, and even the trace metal values, they might not give you any confirmative information. But isotopes, they give us very very trustable information. They show us how mixing is happening, because radiogenic signatures, they can change only when first if is a radioactive decay. Okay. So, radioactive decay is causing that increment, or second of all there is mixing between two different sources with different radiogenic signatures. So, that can cause these kind of radiogenic signatures, because here we are talking about water mixing, okay, water masses that are mixing. So, neodymium is an extremely helpful tracer to understand how how ocean currents has been mixed in the present day, and also within the few past 100 or 200 million years, how stable it has been. Okay, what are the particular regions which is behaving very differently, particular ocean masses that behave very differently. Okay. So, this as we can see that different isotope systems, they have different applicability, right. The strontium isotope system being more homogenized in the global ocean, they gave us understanding more of Earth's history, okay, more of Earth's past history for 600 million years. But neodymium isotopes, they give us evidence of more recent events, recent meaning in the terms of 400 to 900 million years, how things have changed in this particular time scale. Okay. So, particularly through the ocean, how different ocean masses are mixing, interacting or behaving separately. Okay. This kind of information we are having of the modern era. Okay. Modern era means of the last few hundred years. And this rubidium strontium system and the samarium neodymium system, since they have opposite signatures, okay, the crust being more radiogenic strontium, but more unradiogenic neodymium, with the mantle sources being more unradiogenic strontium and more radiogenic neodymium. Since they have this opposite kind of signatures, they have given us enough information about how different rock types of the how different rock types are, and how they have been in the past, and how weathering and basin topography, geomorphological changes has happened in the Earth's history. So, more or less every time you are going to see a paper that is going to report both strontium and neodymium isotopes. Okay. So, they are going to take this, because this two isotope systems, they behave very differently. Okay. They behave very differently, but they show the crustal signature. They will show the crustal signature. So, they will show very different continental crustal signature, and if we are going to study rivers, and if we are going to understand any basin scale changes, then generally both the isotope systems are generally evaluated. Okay. So, as you can see, the crust, okay, the crust will have more radiogenic isotopes. So, this upper continental crust is more radiogenic as compared to the lower continental crust. Okay. This is the continental basalt values. Okay. So, this is the continental basalt values, this is the bulk earth value. Okay. This is the range of values for oceanic islands, and this is the range for MORB, that is upper mantle composition. And as you can see, so this is like having the highest epsilon neodymium, but the lowest strontium, and this upper crust, this has the lowest epsilon neodymium, but the highest 87/86 strontium. So, this is always done simultaneously together, so that we understand how how these differentiations are happening in terms of rocks and basin scale processes, tectonic events, weathering, everything has happened over Earth's history. Now, when we are doing two isotopes at a time, we generally are going to solve these kind of source related problems. Okay, we are going to be dealing with a lot of source related problems. For instance, how much of it is coming from the MORB, how much of it is coming from the upper crust, okay. Where is it mixing with some continental basalts is also providing some of the signals. So, in generally rivers being the integrators, they are going to give us a lot of integrated signals. Okay. So, we have to do what we called is the unmixing. We have to tell how much is coming from where. If this is upper upper crust is giving 70%, the MORB is giving 30%, or 10% contribution is coming from the continental basalt. So, we have to do that kind of unmixing. Okay. So, often we do something called source apportionment. Okay, we are going to do source apportionment studies. So, what we are going to see here, we are going to use these isotope systems. So, we are going to use isotope systems, okay, and we are going to get signatures of a lot of different things. So, for example, this particular study, this particular plot taken from this particular study, we have seen different spring and tributaries, rivers have different kinds of signatures. Okay. And there can be weathering of clay minerals, there can be weathering of carbonates, there can be weathering of glacier moraines and all that. So, different kinds of contributions are coming, and different there is a lot of temporal differentiation, there is a lot of seasonal differentiation, there is a lot of tributary wise differentiations also noted by this particular author. And often we find such studies where we have to determine, okay, how much contribution in that particular river is coming from clay, how much is coming from carbonate, how much is coming from maybe silicate weathering and some other kind of weathering. So, these are the sources and this is my data. So, I want to find how much is coming from where. So, we have to do some kind of source apportionment. For this kind of source apportionment studies, we are going to use particular traces, particular ratios, particular kind of calculations, and such such kind of back calculation. So, we are going to have a signature of a particular river or a particular place, that is a rock geology, and then we have to say how much in that particular river is being contributed from the weathering of different types of rock types. So, this is what is called the inverse modeling type. Okay, we are going to go into what is called the inverse modeling. Inverse meaning we have the final product we know. Now, we have to go back to the source. We want to understand how the sources are. So, this is called the inverse modeling. Forward modeling is what? Forward modeling is where we know the sources, we know how much contributions from those sources are going, and we give the final value. So, this is the source, this is how much each source is contributing. So, here is the final value. So, that is forward modeling. In backward modeling, we know only the end product, we have to go back to the sources. So, this is called inverse modeling. Okay. And geochemistry, this has its most applications in source apportionment, and specifically for isotopes, because isotopes help us segregate these different sources. So, this glacial till has a different isotope signature, carbonate as you see will have a different isotope signature, clay will have a different isotope signature. So, isotope geochemistry is extremely useful in separating these different types of minerals, rocks, water, everything. So, it allows us more identification of end members, and a lot of interpretation depends on such kind of understanding. Okay. So, it can be river and ocean mixing that is happening, it can be a primary liquid and a fractionated. So, if suppose a magma chamber, okay, that is receiving episodic melts. So, after a melt is received, the magma chamber crystals have started forming, but maybe after 10,000 years another melting event, another melt blob as it is called, okay, another melt blob comes and enters that magma chamber. So, now there is another fresh source of magma. So, such kind of more liquid is coming. So, such kind of primary liquid, fractionation that is happening. So, all that kind of unmixing we have to understand, because these kind of studies help us understand about the genesis and how it has formed in the earth's past history. So, we are going to work with particular particular spaces that we are going to use is one is the element plot. So, we are going to plot two elements, okay, on the x axis and the y axis. So, that is called the element plot. We have the element and the ratio plot, which is something like this, where we have one of the element and we have an isotope ratio. Okay. So, a particular element is there, a particular isotope ratio is there, or we have ratio plots, that is both the axes have isotope ratios. Okay. And we are going to see how we are going to plot this. So, let us imagine two end member mixing, that is called binary mixing. So, we have two end members, that means those two end members are forming a final product. Okay. This is the simplest kind of mixing that can happen. It can be anything. For instance, now we are not going to talk about whether it is minerals, magma, or it is water or river water, groundwater. No, we are just going to talk about mixing. So, in any medium it can happen. It can happen in water medium, it can happen in minerals also. Okay. So, in any particular mineral we are going to find out. So, that is our final target product, and we have our two end members, it is A and this is B, and this A and B has this particular strontium concentration and neodymium concentration and particular isotope signature. So, as you can see, the strontium concentration is 100 and 400, neodymium is 2 and 20. Strontium isotope signature for A is 0.712, for this it is 0.704, neodymium isotope value is 0.511 and 0.513. Okay. So, using this data we have to plot how much it is coming from which, that is giving my final value. Okay. Now, certain points that we need to remember is that the same relationships will apply for major elements as for trace elements which are of conservative nature. Now, mostly major elements are conservative. What do I mean by conservative? That means their sum remains stable. Okay. The sum, the fraction coming from B plus the fraction coming from B, they are stable, and that is equal to 100% fraction. When does it become non-conservative? Non-conservative means after mixing there are certain processes which can remove it from the mineral or the water. For example, okay, take an element, say suppose we take iron. Okay. Now, iron is one thing, is it is a sensitive to organics. Okay, it is sensitive to biotic interactions. Okay, biotic interactions, that means it can be uptaken by biota, right. Also, it is redox sensitive. Okay, that means redox alterations can change iron concentration. So, when we are selecting elements for such mixing calculation, we always have to keep in mind that we use the conservative elements and we do not use non-conservative elements. Okay. You will see in mixing related problems, the only tracers that are used are conservative tracers. Okay. Because for them we know that their sum is equal to 1, otherwise even after mixing, for instance for iron, even if it is mixing, it can get removed due to redox related changes or due to biotic and organic interaction. Okay. So, we do not want to fall for such complexities, we are going to use traces which are conservative. Okay. And the same relationships will apply for ratios of major elements, ratios of trace element concentrations, and the ratio of isotopes. So, let us start seeing the first type of space that we are going to see is that where we are going to plot one element versus another element. Now, binary mixing in the concentration space always produces straight lines, and I am going to explain why. So, the first thing that we are going to assume for binary mixing to be correct is that there are two end members with two fractions coming. So, fraction F A from this end member A and fraction B from this end member B, such that this is the entire fraction. So, fraction of A plus fraction of B is my 100%. There is no other contribution from any other source. So, when I am having a mixed signature, so this is my strontium mix. So, my strontium mix is going to have fraction coming from strontium, and since F A is equal to 1 minus F B, I am going to remove that F A term and I am going to write 1 minus F B into strontium F A. So, basically that is F B into strontium of B plus F A into strontium of A. This is the term. So, instead of F A, I am changing it with 1 minus F B. Same thing we do with neodymium. F B of neodymium B plus 1 minus F B into neodymium B. Why do we want to remove F A term? We have less, we want to have less number of unknowns, right. Generally, we have to find both this, we have to write F A and F B, both we have to find. But since we already know that F A is equal to F B, we are going to use it as a substitution for F A term, and now we have only one unknown in this equation, that is F B. Now, we are going to solve for this F B term. Okay. Our idea is to solve for this F B term. So, using substitution and all, what are we going to do? We start dividing. Okay, let us divide this. So, strontium mix minus strontium A. So, in this equation, okay, let us consider this as equation 1 and let us consider this as equation 2. Okay. Now, in these equations, if I divide the first equation with the second equation, so I am dividing equation 1 with my equation 2. So, in my numerator, I have strontium mix minus strontium of A, that is this, and that is divided by neodymium mix minus neodymium A. Again, if I just put a line, so I have F B of strontium B minus strontium A, and here also divided by F B into neodymium B minus neodymium A. So, here I can easily take out my F B term and I am left with only this term. Okay. And if I take this entire term from here to opposite side of the equal to sign, I am finally left with this equation. I am finally left with this equation, right. So, if I am going to plot a particular biplot, so I am having neodymium in one axis and strontium in another axis. Okay, I am having neodymium and strontium and I plot the data, I am going to see that this is in this kind of form where it is basically y is equal to mx. Okay, and here m is this particular value. Okay. So, it is equation of a line. This equation of a line has a slope, that is strontium B minus strontium A divided by neodymium of B minus neodymium of A. Okay. And as you can see that depending on the fractions how it can change. Okay. So, this is fraction of B. Okay. So, this is our end member A and B, and this is how it is going to look for the different fractions. So, when you are going to plot your data, if your data plots here, you go back, okay, and you find out what is the fraction from this particular slope. Using this particular slope, you are going to find out what is the fraction, okay, because in your sample you are going to calculate a particular neodymium value and you are going to calculate a particular strontium value. So, they are going to give you this data, okay, you are going to reach here. So, from the slope of the line, okay, from the slope of the line you are going to able to calculate what is the fraction of a particular component, and if you subtract it from 1 you are going to get the fraction of the other component. Okay. So, this is how we do unmixing. With this I stop in this lecture and we are going to discuss more about mixing theory in our next lecture. Thank you.